So, welcome to problem solving session for Introduction to Group Theory. I am Siddhi Balu Ambore from IIT Gandhinagar, and today we will discuss problems related to syllabus from week 3, that is problems related to some elementary number theory, order of an element in a group, cyclic group and its subgroup, and characterization of cyclic groups. Okay, so let us start with our first problem. Question: let f of n is equal to n power 4 plus 1 for n greater than 1. Then we have these following options. A, that is f of n is always a composite number. B, f of n is prime for at least one n. C, f of n is composite for finitely many n. And D is that f of n is always a prime number. So this is the question they are asking. So I hope you all know what composite and prime numbers mean. Okay, and they are asking whether this f of n, that is n power 4 plus 1 with n greater than 1, we have to check whether it is always so we have to check what the numbers which are coming as an image of this f, whether they are prime or composite or what kind of numbers they are. So that's this question is asking us. And so any guesses which one, or there could be multiple options which can be true. So f of 1 n is always composite number. So n is greater than 1. So let's just check what is f of 2. So f of 2 is 2 power 4 plus 1, that is 16 plus 1. So 17. So this is prime. So f of n is always a composite number is anyway false, because see, f of 2 is prime, hence a is false, because f of 2, since f of 2 is equal to 7, is a prime number. Okay, so I hope this is okay. We just have to check. And so A is wrong. A is not correct. Now they are asking whether f of n is a prime for at least one n. So yes, for n is equal to 2, f of n is prime. Hence, B is correct. Okay, so this one is correct. I hope there are no doubts in this. So we just wanted to check whether it is always composite. So we got one n for which it is a prime number. So we can remove this. I mean, we can declare that A is false because we got at least one n for which f of n is a prime number. And then they're asking whether f of n is prime for at least one n. Well, yes, for n is equal to 2 itself, we got that f of n is a prime number. So let us check for C. F of n is always a composite for finitely many n. So so is it true that f of n is always composite only for finitely many n? Can you prove this, or do you have any counter examples, or how can you say that f of n is always composite only for finitely many n? Any guesses for this? Okay, so see, f of n is what? For C, f of n is n power 4 plus 1. Okay, so if when n is odd, n power 4 is odd, right? This much is clear. N is odd. This implies f of n is odd. So the moment I have, sorry, not f of n power 4 is odd. So n power 4 plus 1 is even for every odd n, right? Because this is odd. So this whole thing becomes even. So the moment I have n as odd number, this n power 4 plus 1 becomes even number. And the moment it becomes even number, I get that it is a composite number because I can divide, I mean 2 is a multiple of this f of n in that case. So therefore f of n is even and hence a composite number for n odd. And since there are infinitely many odd numbers, we get that f of n is composite for infinitely many n. So this statement that f of n is composite for finitely many n is wrong. Okay, so this is not true. We got that for each odd number, for each odd n, f of n is always composite. It is even number. Is this clear? Please write it in the chat that you are following or if there is any doubt. Okay. So, and last one is f of n is always a prime number. So, can you guess, will f of n always be a prime number? It's anyway false, right? We got that f of n is composite for odd. So, it can never always be prime number. For example, take f of 3. F of 3 will be what? 3 power 4 plus 1. So, it is 81 plus 1, 82. So, it's not always not prime. So, therefore C false, therefore D false. Okay, so this one is also not correct. It's not always prime. Okay, so this f of n is not always composite or not always prime, but it has at least one n for which it is a prime, and again it is composite for infinitely many n. Okay, so I hope this was okay. Okay, I hope that no was to say that fourth one is false. Okay, so next one we will try this. Question 2. Let f of n is equal to n square plus n plus 41 for n greater than equal to 1. Then A, that f of n is always, again, the same kind of question, is always composite. F of n is always a prime number. C, f of n is even for infinitely many n. And D, f of n is always odd. Any guesses for this? Which one you think that is correct and is false or so on? See, f of n is this. What is f of 1? F of 1 is 1 square plus 1 plus 41, that is 43. F of 2 is 2 square plus 2 plus 41. This is 47. So f of n is not always composite, right? So this is prime. This is also a prime number. So f of n is definitely not always composite. It is prime. I mean, we got at least one n for which it is prime. So f of n is not always composite. So first one is false. Now f of n is always a prime number. Can someone tell me I mean, do you think that f of n is always a prime? Because see, f of 1 is prime, f of 2 is prime, f of 3 square plus 3 plus 41, 12. So it is 53. Is it possible for this to be always a prime? Can you give me one n where it is not a prime? For it is not prime. For f of 4 is what? 4 square plus 4 plus 41. 4 square plus 4 plus 41 is 16 plus 4, 20. 61. Is 61 prime? It is prime, right? So, so see, the simplest is here we have 41. So f of 41 will be what? 41 square plus 41 plus 41. So this will be what? 41 plus 1 plus 1, 41. So we get 41 into 43. Okay, so f of 41. Okay. F of 11. What is f of 11? 11 will be 121 plus 11 plus 41. Yeah, I don't think this will be composite number. It is 3. It is 173 upper 3. Yeah, it is 173. 173 is a prime, I guess. You can check. This f of n is prime for n n less than equal to 39. And even at 40, this becomes non-prime. You can check that. F of 41 is composite number. So see, if whenever you have some function of this kind, some n power k plus whatever here, plus some alpha, or not alpha, but maybe some, not p, yeah, p maybe. If whenever you have such kind of function where there are some terms, let me write this in form a1 nk1, nk plus ak n power k plus plus so on a1 n plus a naught. This is my f of n. So if a naught is 1, then we can't conclude anything right at the beginning. Or there might be some properties of this function which can make it look like that it is always prime and so on and whatnot. But the moment you have a naught not equal to 1, this f of a naught will always have a naught as a factor. A naught into this will be ak n into k minus 1, so on, plus a1 here. Not even a naught. This is a naught. This always factors. So the moment you have such kind of functions where there is this number which is standing alone, you can always, there is at least one n for which this function will be composite. And the moment you have one, there are infinitely many. You, for example, here 41 is there. You take all the multiples of 41. Okay, for 82 also you can take out 41. For each multiple of 41, you will have composite. So the moment you have one composite number, you have almost infinitely many. At least in this case, such kind of examples, you can have that. So is this okay? So this is always a prime is not correct statement. Is this okay? Yeah. Now next option is that Fn is even for infinitely many n. So what is F again? What is Fn? Fn is n square plus n plus 41. So I can write this as n plus 1 plus 41, right? And this for every n plus 1 is always even. So this f of n, that is n plus 1 plus 41, will always be odd for every n greater than equal to 1. This is true, right? I can write this n square plus 1 as n plus 1 plus 41. N plus 1 is always even. So when I add 41 to it, it will always be odd. So this f of n is even for infinitely many n is completely false. And the last option, that fn is always odd, is true. We just saw that fn is always odd. Is there any doubt here? This you can please keep in mind. Okay, this might be helpful if you are also appearing for the exam for this course. Okay, that if you have such kind, this is important here. This a not, let me not use this one, not this one. This a naught here is important to have this standalone a naught here not equal to 1. If I have 1, I can't really say anything about it, that it will be composite or prime or anything, because you can't take one. I mean, you even, one taking one common is not helping us to prove anything. So yeah, but a naught not equal to 1, if it is there, you can say that it will be composite for at least one n equal, and that n is specific, this particular a naught. Okay, so I hope this was okay. Let us move to next question. Question 3. The number of generators of cyclic group Z mod 225 is first 120, 1, 225, and fourth is 25. So any guesses for this? One 120. Yeah, it's correct. So see, in Zn, so in Z mod Nz, order of any A in this Z mod NZ is n by GCD of A comma n, right? So if I want to have, this is cyclic group. So every element which has, so this is cyclic group with order 225. So any cyclic group of size M will have generators. So every element of that group of size M, the generators will be elements whose orders are M. So there could be many different elements which can generate the same group. So if order of G, if G is a cyclic group with order of G, or this is some, let me write N, then if A belongs to G is such that order of A is N, then A generates this, then A generates G. Okay, so that's what we are trying to do here. Here we want elements which, so if I want order of A to be N so that it can generate my group Zn, I must have this GCD of A comma N to be 1. Then only I will have this, or this, then only my A will generate my group Z quotiented by NZ. Okay, so therefore A G is equal, so what would, how to write this? So therefore number of generators of Z is cardinality of all those M in N such that GCD, or in fact not even this M, we can take this N and this with G M less than equal to N, and GCD M comma N is 1. Is this okay? So this is nothing but Euler function, if you know. Okay, and formula for this is this N into product of P dividing N 1 minus 1 by P. Okay, and if when I write this as P1 K1, Pn Kn, then this is P1 power K1 minus 1, P1 minus 1, so on. Pn Kn minus 1, P, not N, let me not write this N, PR maybe, PR minus 1. Okay, this is the formula. So we have here GCD. Let me write it. This was general. Let me write this. So therefore, what I need to find is phi of 225, which is 225 is what? 15 square. So it is 3 square into 5 square. So this is 225. 3 square into 5 square into 1 minus 1 by 3, 1 minus 1 by 5. And this is 3 into 5 into 2 into 4. And this is 120 as suggested by Dr. Amit. So this formula, please keep in mind this one, number of this Pn, and Pn is nothing but this function. So you can directly, and this formula is also important in order to find order of element in a Zn or in any cyclic group to start with. Any cyclic group of finite order. Okay, so I hope this was okay so far. Any doubt here? Okay, if not, then we'll move to next question. Question 4, that the greatest common divisor of 42823 and 6409 is, option is 1, 17, 23, D is 39. This is the question we have. We have to find the GCD of these two numbers. GCD of, so in short, we have to find GCD of 48223, yeah, and 6409. How to proceed? Any guesses or any? So there is algorithm to find GCD of given numbers, right? So it's like if I have to find GCD of A comma B with A greater than B. So what I do is I start with, so since A is bigger, I divide A by B, and then yes, it is. So then there is some co- there is some Q1 which we will get here as a multiple, and there will be some reminder R1 here. Okay, and so what we do is in next step, if this R1 is 0, then this B becomes my GCD. If R1 is 0, then GCD of A comma B is B, and we are done. But if this R1 is non-zero, then what I do is I take this R1, and now note that this R1 is a remainder when I'm dividing A by B. So this R1 will either be 0 or it will be less than B. So this R1 is now less than B. So I will divide this R1 by B. Then there will be some Q2 here, and there will again be some remainder R2. So if R2 is 0, then I can say that this R1 is my GCD. If not, then this R1 will be less than R2 will be less than R1, and again I proceed like this. And note that this process will stop because every time I'm moving in next step, my B and R1 both are decreasing. I mean, not B and R1, but my R1, my reminders are decreasing. And so does the previous, this both Rn and here Rn minus 1. This will be some, let me write one more step. For example, now R1 is less than R2. So I divide R1, R1 by R2. There will be some quotient here, and this will again be some R3, which either be 0 or it will be less than this R2. And I process. I continue this process, and I get that there will be some Rn such that this n minus 1, this un plus 1, and then such that this Rn will be 0, and then this Rn will be my GCD. So this GCD of A comma B will be my Rn. Okay. I mean, it doesn't look very neat and easy, but yes, this is the process one can follow to get to find the GCD of given numbers. Okay, so we will do the same thing. We will start with finding GCD of these two numbers, and we will follow the same division algorithm. Okay, so we have to divide this 6409 by this 42823, and let me just write this. And this is 4369. Okay, I mean, division is, I assume you all know division, okay? And similarly, now you have to do is, this is non-zero. So we have to multiply now by this 4269 by 6409. I mean, just to get the flavor of this, let me just write this. If I want to find GCD of given me two numbers, for example, 12 and 16. Okay, just to check whether this algorithm works. So what I will do is I will divide 12 by 16. This will be 1, 12, 4. Now I will divide 12 by 4. So 4, 12, and I get 0. So GCD, so here I got 4 such that remainder is 0. So GCD of 12 and 16 we anyway know is 4. Now let us try to find GCD of something like maybe 7 and 5. So if I try to find GCD of 7 and 5, so if I take 5 divided by 7, I will get 2 here. And when I 2 divided by 5, I will get 1 here. And then again I will do what? Here 2 and 1. This is again not 0. So I will now divide 1 by 2. So 1. So GCD of 7 and 5 is 1, as we know. So just to give you the idea that this algorithm works, I just started it with very small numbers just to show that, yeah, and this will be 0. So go till the last step where the remainder is 0, and you will get this because we are reducing the numbers and we are working with only positive numbers, I mean natural numbers here to find this GCD. Okay, and just for the sake of completion, let me write this immediately. This 4369. Most of them are just big numbers where you don't even need to uh, do the actual calculation, just subtraction by previous number and oh no, 43, right? So it will be 80, 40, 239. And now this 239, not 239, wait, 8, 289. And this is 2040, this is 2023, and here it is 7. And I get 17, and 17 divided by 289 is 17,289, and I get 0. Okay, so therefore GCD of this two numbers 48623, no, it's not this number, 42823 and 6409 is 17. Okay, so this number here is my GCD. Any doubts here how the algorithm works? Here it is 2. Anyone has any doubt about the algorithm? Or you saw this algorithm before? If not, then please try to find the GCD using this algorithm of known numbers where you know what the GCD will be, and try to practice this, because such questions are helpful to solve this kind of questions where we have to find the order of some element in cyclic group. In that case, this denominator is GCD. So you must know how to calculate GCD in order to solve such kind of question we have where we have to find order of some element in a cyclic group and so on. Okay, so now this next question, I think it's question number 5. That let G be a group, then we have to check which of the following are true. So we might have multiple options correct. Okay, so first one is that if G is an infinite group, then any subgroup of G is also an infinite group. So I'll be writing all the 4 options. Meanwhile, you just start thinking about the options which I have already written. So if now second, if G is an infinite cyclic group, then any non-trivial subgroup of G is also an infinite cyclic group. Okay, so this is another question, that if G is an infinite cyclic group, then any non-trivial subgroup of G is also infinite cyclic group. Okay. Third one is that if any non-trivial proper subgroup of G is an infinite cyclic group, then G is an infinite cyclic group. Just a second. Okay, so if any non-trivial proper subgroup of G is an infinite cyclic group, then G is an infinite cyclic group. And we either need to prove these statements or we have to give the counter examples. So whatever is your guess, please try to work in that direction. I'm making these options visible to all. Is finite. If G is finite and let me just write it here. And any proper subgroup of G is cyclic group, then G is a cyclic group. So any guesses which one is true, which one is false, and so on. First, let us start with the first one. What is your guess? That G is an infinite group, then any subgroup of G is also an infinite group. Is this always true? That every subgroup of infinite group is always infinite? Can you give me, if this is true, then Any non-trivial, let us write non-trivial, otherwise this won't hold anyway. Okay, so if G is an infinite group, then any non-trivial subgroup of G is also an infinite, because see, trivial group, that is just group containing identity element, is a subgroup, and which is also like finite order group containing only one finite order subgroup which contains only one element. So let us add this, that it is non-trivial subgroup of G. Then is it always an infinite group? G is an infinite group, then any non-trivial subgroup of G is also an infinite group. Any counter examples? We saw many examples so far in our previous lectures. Can you come up with any example, or you have no idea? So let me give you this example. So this statement is not true, okay? This is not true at all. And the example we can take, first one is this GL2R. Okay, and with this matrix multiplication. So now that I have given G, can you give me some H? We can take any cyclic group. We want to find an element A in this G, that is this GL2R, such that it's like if I multiply it finitely many times, I need to get identity matrix. So can you give me one example where this holds? One matrix. This matrix, right? If I take H generated by this, so this H only contains these two elements, minus 1, 0, 1. And inverse of this matrix is the matrix itself and this, right? So cardinality of H is only 2. So therefore, H is, therefore A is false. Therefore, G is infinite, but subgroup H of G is finite. Therefore, A is false. Okay, so this A is not correct. Subgroup of infinite group need not be, non-trivial subgroup of infinite group need not be infinite group. I hope this was okay. If this example is too much, we can also take this, right? G to be R star, comma Z, comma with multiplication. This is infinite group, right? This group, I hope you all know. This is all this multiplicative group of R, and here identity is 1. Okay, here, yeah, identity is 1. It is multiplicative group, and you can take then H is this minus 1, 1. Okay, and this is again group, and in this R star, and this is of order of, and this is non-trivial group. Okay, this is non-trivial. Here also this was non-trivial. Okay, and here also order of H is 2, G is infinite. And H is finite group, finite subgroup of G. And you can now create many such example where G is actually infinite group, but my H, that is subgroup of G, that is finite. Okay, so first one is not true. Now second one, if G is an infinite cyclic group, then any non-trivial subgroup of G is also infinite cyclic group. So what is your guess for this one? This, that if G is infinite cyclic group, Then any non-trivial subgroup of G is also infinite cyclic group. What is your guess for this? Is this true? Is this false? Or you have no guess? Anyone? Okay. So this statement is true. First of all, what is given is G is infinite cyclic, and given that G is infinite cyclic group. And what we have to check is that if every what every non-trivial subgroup of G is infinite cyclic. So any guesses? So first of all, if you remember in our last lecture, last live session, we saw that subgroup of any cyclic group is always cyclic. If you remember, we saw that subgroup subgroup of any cyclic group is also a cyclic group. So cyclic part is clear here, that every non-trivial subgroup of G, it will be cyclic group. Okay, but now what we have to check is whether that cyclic group is also infinite or not. Okay, so given that G is, let G is a power, G is generated by A, and A power n is not 1 or E. Let me write 1 here for any n greater than equal to 1. This is how we can characterize G being cyclic and infinitely generated. Okay. And okay, so if H is subgroup of G, then H is of this form, right? That H is generated by A power m for some m greater than n. H is non-trivial. Let me write it as non-trivial. Okay. Then I can write that m is strictly greater than 1 here. Okay. So we saw that, okay, and this m is the smallest positive m which belongs to this H. We also saw the expression. Okay, in order to prove that every subgroup of a cyclic group is cyclic, we started with the m which is least in that H. Okay, and we said that H is a subgroup of G. So every element of H is of the form A power m or some m, and then we chose the least positive m from that H, and we proved that this A power m itself generate my entire H, and H becomes cyclic. Okay, that's what we did last time when we solved, we proved that subgroup of a cyclic group is a cyclic. Okay, so this is A power m for some m greater than 1, and we can assume this m to be least and whatnot, as per your choice. But if H is finite subgroup, this implies that A power m power k will be 1 for some k in n, right? This, for cyclic finite groups, this is what we have. After certain stage, these powers of m repeat and a power m, a power k becomes 1 for some k. So this imply what? A power mk is 1, right? But this is contradiction since g was infinite and a power n as a power n is not equal to 1 for any n greater than equal to 1. Okay, this a is same a which we started with. I hope this is clear. Any doubt for this one? No, right? Great. So, yes. So, again, we started with A, and since A is infinite, this holds. But again, the generator of H is of this form. But if H is finite, if finite, then this A power mk becomes 1, and it contradicts this. If I make this star, it contradicts star. Okay, so this one. So in fact, what they said that then this implies that therefore H is an infinite group. Infinite cyclic is anyway there. Infinite cyclic subgroup of G. Okay, so this always holds. So this B is true. Okay, B is true always. We just proved that. So now C part. C is that if any non-trivial, so given that, okay, so what they have given in this case that any non-trivial subgroup of G is an infinite there is a non-trivial subgroup of G which is infinite cyclic group, then to check G is an infinite cyclic group. So if G has, so earlier what they said was if G is infinite cyclic group, then every subgroup of G is also infinite cyclic group. Now what they are saying is if we have a non-trivial subgroup of G which is infinite cyclic group, then can we say that G is also infinite cyclic group? So see, G has a subgroup which is infinite cyclic. So infinite group condition is always there with us. Now we have to check whether that subgroup being cyclic will give us that G is cyclic or not. Is this always true? That every non-trivial proper subgroup of G is cyclic, then G is also cyclic. No, right? Yeah. Can you give me an example? So as suggested by someone, it's not true. But can you give me an example? We can take this, okay? So let G is equal to R plus. This is infinite group, okay? And this Z plus is infinite cyclic group in R, if you understand this. Is this okay? But R plus is not cyclic group. I hope you all understand that R plus is not cyclic group. Z plus is cyclic group generated by 1. R under addition is not cyclic group. Okay, because if it is cyclic group, then if do you have any argument to prove that this is not cyclic group? What will happen if this becomes a cyclic group? See, so if R is cyclic, R comma plus is cyclic group, okay, then what will happen? Then R plus will be some, or R is equal to some X, right? Where X is in R. So this is under cyclic group. Okay, we are considering R as a cyclic group. So this will imply that R is some nx for n in n. But is this true? The moment, note that this x is not 0 anyway, because 0 is the identity of group. So this anyway is not 0. But the moment I have non-zero x, which is in R, this x by 2 also belongs to R, right? But I mean, this x by 2 is not equal to mx for any m in n. So this is not possible. Forget about this 2. I mean, any n where n and n greater than 1. Is this true? I mean, is it clear that this is not possible? If R is generated by some x under addition, then this will be there, and this is not possible. Then x by 2, which will be in R, but it won't be generated by this x. It is not some integer multiple. Oh, not n. It must be in Z. Some integer multiple of, let me again write here, m in Z as well. Okay. Is this okay? And x is non-zero. We have already assumed this here. For x non-zero. Any doubts, please let me know. If there are no doubts, I will then move on to next question. Okay. So this question we will try to answer now. This is question 6. That any group of order 89 is cyclic. We have to check whether this is true or false. Can you guess whether this is true? What is 89? 89 is a prime number, okay? So 89 is prime if you don't know. Then we know that any group of prime order is always cyclic. Okay. Any group of prime order, just like, is always cyclic. Okay, so 89 is prime, so this anyway becomes true. So that's why this is true. Okay. I hope you all know this, that any group of prime order is always cyclic. You can try to prove this. Okay. And one more. Now these are few easy questions, but you can try that. GCD of A comma B is GCD of A comma C implies that LCM of A comma B is equal to LCM of A comma C. This is again true or false. Any cases for this? Is this always true? The moment I have GCD of A and B and GCD of A and C, let me just write this. A, B, C are natural numbers. Can this be true? Note that this LCM of, it's false, right? LCM of the AB is what? AB by GCD A comma B. Okay. And this is not true because even if GCD is same, this AB here is different, right? So even if this AB here makes difference, so I can alright GCD of A comma B is equal to LCM A comma B, and this is equal to, as they said, GCD A comma C, and which is AC by LCM A comma C. And this need not be true. I mean, AC, let me just give you count example. For example, A, B, and C are this. Then GCD of this 3, 5 and GCD of 3, 7 is 1. Okay, but LCM of 3, 5 is 15 and LCM of 3, 7 is 21. Okay, so this is not true. Yes, exactly, 3, 5, 7 as suggested. So this is not true, okay? I mean, this statement is false. And you can try this, and now this question which we already discussed formula for, that This is question 8 now. The order of 6 bar in group Z mod 10Z is, we have to find. So I already wrote this before that for cyclic group G with order of Gn, for A in G, order of A is this n divided by GCD of. Okay, so when I say this A in n, this cyclic group, so G is generated by some A. So any element X in G, X is of the form this A power K, right? Then order of this X is n by GCD of this K comma n. Okay, this is the formula which we have. So again, so what we have here, 6 bar in 10Z. So order of 6 bar will be 10 by GCD of 6 comma 10, which is 10 by 2, so 5. So can we check whether it's 5? So 6 plus 6, 12. And then, yeah, I mean 12, 18, 24, and then 30, which will give me in Z mod 10Z as 5. Okay, you can try this. And now this question. Question 9. For A belongs to Z mod 36Z, define a function P of A. Now this function is from Z mod 48Z to Z mod 36Z by 1 bar here going to A bar. So this is cyclic group. So 1 bar generates this, and in order to get the information about entire group homomorphism, it is enough to send the generator of that group. I mean, it's enough to define the function on the generators of group, and the property of group homomorphism will give us information about what value function holds for any given element in that group. So this 1 bar going to A bar, and now they are asking for which values of A, I mean value or values of A, the map phi A defines a group homomorphism. And options are A is equal to 10, B that A is equal to 9, C A is equal to 1, and D A is equal to 6. So how to start with this? See, we are in cyclic groups. All the information we have about cyclic group is the order of the group and order of the elements of the group. And one thing which is important to understand is that if G is a group homomorphism, then for every A in G, order of, let me, group homomorphism, if F is a group homomorphism, or let me write this. Let F from G to H be a group homomorphism, then order of, then for every A in G, order of F of A divides order of A. Okay. And it divides order of A, and so this also it will imply this also divides order of G, because order of A anyway divides order of G. So this is just the extra information we are gathering here, just to help us try to solve this question. So if I send this 1 bar to A bar, so see, order of 1 bar is 48. Okay, so order of 1 bar is 48. Okay, and what they are saying is, now I want to send 1 bar to A bar. So if I have to send, so if I send 1 bar to 10 bar, so this is in, let me write it here, in Z mod 48Z, in Z mod 36Z. Any guesses, please? Now 1 bar, if I send 1 bar to 10 bar, what is order of 10 bar in Z mod 36? This is what, 36 by GCD of 10 comma 36, and it is, this is 2 into 5, this is 6 into 6. So this is 2 square into 3 square, right? So GCD of 10 and 36 is 2. So this is 18. So here order is 48 and here order is 18. Do they divide? I mean, is this happening in this case? This order of f of A. So order of f of 1 dividing order of 1. That is 18 dividing 48. Is this true? This is not true, right? This is not true. Okay, we will only be using this criteria here. Order of f of A divides order of A or not. Here 1 is going to A bar. So I just have to check whether this order of 1 bar divides, sorry, order of f of 1 bar or this phi A. Doesn't matter. Let me write here phi A. Order of phi A of 1 divides order of 1 or not. So that is order of 10 bar dividing order of 1 bar or not. This is in Z mod 36Z and this is in Z mod 48Z. Okay, so this is happening. So this does not divide, not true. So therefore phi 10 Z mod 48Z, yeah, 48Z to Z mod 36Z is not a group homomorphism. Okay, is this clear? Now we have to go to A is equal to 9. So now I'm sending my 1 bar to 9 bar. So order of 9 bar is what? Is 4, right? Directly, I mean, we are in Z mod 36. So order of 9 bar must be 4. 9, 9, 18, then 27, 36. Order of 9 bar is 48. You don't need to have this GCD formula for that. So now is order of this 9 bar divides order of 1 bar in Z48. That is just 4 divide 48. This is true. So I can conclude that sending A to 9 bar will give me group homomorphism. Is this clear? So therefore, phi of 9 from Z48 to Z36Z, 1 bar going to 9 bar is a group homomorphism. Is this clear? We have to check for 2 more. But I hope you all are understanding like what exactly we are doing here. Okay. Now C part. C is, so this one is there, this one is not. C is sending 1 bar to 1 bar. So C, this was B part, this was A part here. So I am sending 1 bar to 1 bar. So, but order of 1 bar in 30 Z mod 36 is 36. Okay. So is this true? Order of 1 bar divides order of 1 bar. This in Z mod 48Z. So, which is 48. So, do we have this? No. So, therefore, 1 bar to 1 bar, phi of 1 bar from Z mod 48Z to Z mod 36Z is not a group homomorphism. Okay, now D part. Now we are sending 1 bar to 6 bar. And any cases for this? Order of 6 bar in Z mod 36Z is 6. So do we have, so order of 6 bar divides order of 1 bar, that is 6 divides 48. This is true, right? So this is true. True. Therefore, P of 6 bar such that Z mod 48Z to Z mod 36Z is a group homomorphism. Okay, so all we did was we used this information that if F is from H, G to H, a group homomorphism, then in that case, we have this F of A divides order of A. And why does this happen? Because this is group homomorphism. And in group homomorphism, what we have is that E of G goes to E of H. This is there always. Okay, there might be many other elements which are going to E of H, but the identity of group G must go to identity of group H. Okay, and so if order of A is such that, so if A power n is identity of G, then under this group homomorphism, F of A power n must also be identity in H. So F of A power n is 1H. And if this is happening, if for some n, F of A is becoming 1, then order of F of A must divide this n. Okay, so I hope this is clear. So, any doubts here? Like why this statement holds that order of f of a divides order of a? And this is the only criteria which we use to solve this entire question. So we saw that one was not helping, but six gave that this PA is a group homomorphism. So let us move to next question. This question, this is question number 10. If G is a cyclic group, then check. And the first one is that if G infinite, then there exists exactly one generator of G. B is that if G is infinite, then there exists exactly two generators of G. C part is that if G is finite and G is not isomorphic to Z mod 2Z, then there exist at least two generators of G. And D part that there exists a subgroup H of G, so that every element H in H satisfies all of H is H. Okay, so any guesses for this? Which one is true? Or which are all true? Or which one is false? So G is infinite, okay? First, G is infinite, then there exists exactly one generator of G. So can you give me a cyclic group which is infinite, which has exactly one generator? Is this possible? Simply take this, our norm, this Z plus. We know that Z plus is cyclic. A and B as infinite cyclic group should be infinite cyclic subgroup. Thus, they have infinite generator, must have two. Yeah, exactly. See, okay. So first of all, first one is wrong. That is guessed by many of you. That A is definitely not true because see, Z is cyclic and Z is cyclic generated by 1. So therefore, Z 1 is generator of Z, but also if you see minus 1 is also generator of Z. This is correct, right? Minus 1 is also generator of Z. Yes, exactly. As Ajit said that it will have two. The moment it is infinite, we will see the third part also. Second part that there exists exactly two generators. Why? So definitely first one is not true because minus 1 is also generator of Z. Try to understand that. Right? Because Z is what? M into 1 such that M in Z. So right. So and this is what? M into minus 1 M in Z. These two, both these sets are equal. Okay, you can check. When we have negative here, we get multiples of minus 1, and when we have positive here, sorry, negative here, we get generators of positives of here. I hope you understand what I'm trying to say here. So this is definitely, this is cyclic subgroup of infinite order, but it does not have only one generator. So now, as they said, let me write this properly, okay? Infinite. So G is now infinite. So G, suppose G is a power n for some, not a power n. Okay, G is this and a power n is equal to 1 for not equal to 1 for any n in natural numbers. Okay. So see, every element of this G is of this form. And A inverse also definitely generates this. So if element generates, its inverse also generate that subgroup. Okay. So this is there. If some element generates, then its inverse also generates that subgroup. So when we have cyclic subgroup, when I write this, G is equal to a power n, n belongs to Z, right? So G is also a inverse power n such that n belongs to Z. Similar argument like this Z minus 1 and Z1. All the positive powers here will be generated by negatives there. All the negatives there will generate positives in this. So these two sets are equal. Okay, so this is there, but now why only two? Can someone give an argument like why only these two generate and no other element of G can generate this? Mhm. No guesses. See, if see any element x in G is of the form a power k some whatever k greater than equal to 1 doesn't matter. If we say that if G is generated by this x, this implies this G is generated by this a power k, right? And the moment I have this, that G generated by a power k and a belongs to G, what I will have? This implies this a power k power n, since G is a cyclic group, this will be equal to a, right? So this will imply what? A power kn is equal to a. And since we are in group, we can cancel. Okay, cancellation holds in group. So this will imply that a power kn minus, or this is not very correct way to write this, but this implies a power kn minus 1 is a. Sorry, is my identity. I can cancel a from both sides. A power kn minus 1 into a is equal to 1 into a. So this kn minus 1 will be my 1. This contradicts the fact that G is an infinite group and was generated by A. So this contradicts. This contradicts the fact that G is an infinite cyclic group generated by A. If it is infinite cyclic group generated by A, then such kind of situation cannot arise. Okay, but if I say that X is something of this sort, then G generated by A power generated by some other X, but that X is of this form, then we will get this condition here, which I have, let me highlight this condition. This is not possible. So therefore, only generators of infinite cyclic group G is equal to A are A and A inverse. Okay, is this okay by you all? I mean, is it understandable? If there are any doubts, please let me know. So this one is true. Okay, there are exactly two. Okay, so yeah, good. Now next C part, that if G is finite, just a second, let me check. Yeah, if G is finite and G is not isomorphic to Z mod 2Z, then there exists at least two generators of G. G is finite is given. Oh, let me write the given condition. G is finite. G is not isomorphic to Z mod 2Z. To check, G has at least two generators. I mean, this This anyway doesn't make any impact as a statement. Because we already proved that. Okay, no. This is no, G is finite is here. Okay. Okay, so G is finite, and so G is generated by A such that A power K is 1. Okay, so what problem in this and earlier case was? What's the difference? Here, the infiniteness of X, not X, G was infinite. That's why when we arrived at this condition, we could say that it contradicts, and that's why it has only two generators. And A inverse are not same. Okay, in infinite case, because if A is equal to A inverse, then this will just say that A square is 1. And this is not there for infinite case. Okay, so to avoid that, even to avoid that, the moment I have this A is equal to A inverse, it won't hold. See, here this is not true because of infinite condition. And here they said that G is not isomorphic to Z mod 2Z. And that will again give me that this A is not equal to A inverse. Is this clear? And using this condition, we will arrive at the stage where we can say that there are at least two distinct generators for this G. Okay. So suppose A power K is N. So if what other element we can choose? So if G is A, then we anyway know G is also A inverse, generated by A inverse. But A is not equal to A inverse, as if A is equal to A inverse, that will imply that A square is E. And this implies that so cyclic group of order 2 will be isomorphic to Z mod 2Z, which is not true in our case. Therefore, G has at least two generators. And in fact, G has, since this is finite cyclic group, all the elements whose order, not order, but so the number of elements which generate G is exactly Pn. So number of generators of G. So let G is A and A power N is 1, and order of G, or let me just write both the notation, is K. Then generators of G is this phi of N. The number of elements whose GCD with one GCD with G, what GCD with A is 1. So order of N. So all the elements will be of this form, right? 1A, 1A, A square, and so on, and A power N. A power N will be this again. So all the elements whose GCD with all the elements whose, so if X is of this form, A power N K, and if GCD of this K and N, let me write R and K is 1, then this A power R, this AR will generate my G. You can check this. Because since the GCD is 1, only after multiplying this, see, order of X is what? This is this K by GCD of R comma K. So the moment I have this GCD of R and K1, I get order of X as K. And the moment I have order of X as K, it will generate my entire group G. So this Z not isomorphic, G not isomorphic to Z mod 2Z is required only for this condition. Okay. And in earlier case, this fact was taken care by the infiniteness case. So we have this both the characterizations of generators of G being cyclic group. Okay, so such that we can say that G is infinite, then there are exactly two generators. Okay, in B case, we proved that there are exactly two generators of G, and this C part we got that if G is a finite cyclic group not isomorphic to Z mod 2Z, then there exist at least two generators of this G. Okay, now the last part that, yeah, we have some time. D is that there exists a subgroup H of G so that every element H in H satisfies order of H is cardinality of H. As when they are writing this is definitely not equal to E. So, do you think that this statement is true? Can we always find such group? Can anyone guess whether this statement is true or false, or any suggestion, I mean any input? Can you try to give me an example at least where this is happening? So what we have is only this information that G is a cyclic group, and then this statement is there. So let us take this Z5, Z mod 5Z. It itself giving me that, okay, there exists a subgroup. So in Z mod 5Z, each element has order 5. So H itself, so if I take G is equal to Z mod 5Z, then H itself gives me G is equal H, that is G, gives the subgroup such that order of H is order of every element is again this H not equal to E is size of that group. So can we try to give such in G is equal to Z mod 6Z? Can you give me an example of H? What H shall I choose in order to have order of every element of this group? of this subgroup of G, each element has size, not size, I mean, each element has order equal to the size of H. So note that since G is a subgroup of H, okay, or if I remove this condition, see, if I remove this condition, then H is equal to identity will always satisfy this condition. There exists subgroup H of G so that every element H in H satisfies order of H is, so this order of E is anyway size of E. So this is anyway true, but in non-trivial case, what can we say? So in Z mod 6Z, 0 bar, see, H must have size either 1, 2, 3 or 6. So if I wanted to take this, what is, then H actually gives me this, right? Size of H is what? 2 and order of 3 bar is 2. Okay, and similarly, if I take H bar is equal to this 0 bar, 2 bar, and it will be 4 bar, right? And order of 2 bar is again 3. Order of 6 bar is, sorry, 4 bar is again 3. So here order of, which is anyway equal to, this is equal to size of H, this is equal to size of H. So can you guess the pattern here? Like what kind of elements are giving me the, what we say, order of H is equal to order of elements, or do you want to try one more example to get the idea? Any guesses from what we discussed so far for this? Or let us do this in some, this example. Can you give me H which works? Or not this? Let us keep some everything odd. Yeah, this one. Can you give me an element? I mean, this group. We are in cyclic, so that's not any problem. Any group which you feel. I hope I'm not going too fast. I hope you are understanding like what I'm trying to say here. Order of H. Can you give me an element? 0 bar is there. Anyway, few more elements. If I take 15 bar and then 45 bar, sorry, 30 bar. Does this work? Order of 15 bar is what? It is 3 bar. Again, similarly, order of 30 bar is again not 3 bar, 3. And order of, which is order of H in this case, this is order of H in this case. So what are the elements which we are which is giving us the, this finite, I mean this condition that order of element is equal to order of the H which we have. So in case, so if in C, what we are getting is in G is A power A and cardinality of G is N, then if P divides N, then X power A power what? N this is 15, which was 45 divided by, yeah, N divided by P will have order, yeah, will have size. Is this clear? P is prime here. Can you all understand this, that this is happening? And the other prime was 5. So if I take 45 divided by 5, what will be? It will be generated by 9 bar, right? Yeah, I will, if I take H is equal to 0 bar, 9 bar, 18 bar, 27, and 36. All the elements have order 5. Can we check? 18, 45, 27, 40, and 36, 45. Yes, all the elements have order 5. Okay, so, and you can check order of H will be P, because that's how we have chosen this N by P. And order of every element. So order of this is what? Order of this A power N by P is N divided by GCD of N comma N by P. So it will be what? See, this P is such that P anyway divides N. So we are just, what we are doing here is, if N was this P1 power K1, PR power KR, and so what we are doing is this PI divides N, then PI divides N, then GCD of N comma N by PI will be what? This everything, P1 power K1, PI power KI minus 1 continues, and PR power KR. So when I apply this formula, A N by P, then this is was N by GCD of this N comma, this everything, P1 power K1, PI power KI minus 1, so on PR. And this is just N divided by this whole thing, this same thing actually. And this is just my PI. So order of this N by PI is PI. And also, since this is prime, no, all the elements will have the same order. Okay, you can check this, that this will happen in this case. This order of HP will be this P and XP will be this P. This is general statement which I made. This will be N by P. This will be just P here. Let me just write again. N is equal to P1 power K1, PR power KR, then for PI dividing N. Is this okay? So this is always there. We can always find this H such that this is happening. Any doubts here? No doubts. Okay. Okay, and one more question which we will try to see here. Again, it is related to that one question which we did earlier. Okay, and it is this. Similar to what we did. So how, if we have this question, I don't know which number it is, question 11. If PA is from Z mod MZ to Z mod NZ, then for how many A, okay, again, I need to write this. If A belongs to Z mod NZ and phi A is such that 1 bar is going to A bar, then what is the number of A in Z mod NZ such that PA is a group homomorphism? Can you all guess? We just saw in earlier case, right? Though 9 and 6 which we got were such that what is your guess for this? See, for any PA from Z mod MZ to NZ, for this to happen, for this, so we are going from 1 to A bar here, right? For this to happen, for PA to be a group homomorphism, we must have order of A bar divides order of 1 bar. That is, order of A bar must divide what we say M here. So this implies that order of A bar will be what? It is n by GCD of A, comma n must divide M. So what that gives me? So it is also, when I say this order of A bar divides M, this implies that A bar power M is 0 in Z mod NZ, right? So these imply what? M divides N, right? So this is like number of A in Z mod Mz such that A power M is 0 bar in Zn. This is the number of A's we have to find. Okay, and can anyone give me the exact number, what it will be? Okay, so you can check that since we are running out of time, you can check that this is like number of A bar such that PA is homomorphism is GCD of this M comma N. Okay, only in that case this will survive. Okay, that this N by GCD M comma N which we wrote here, that will survive. So you can check that it is the same. The 9 bar and 6 bar were elements such that their GCDs, I mean the orders will have, I mean GCD in that case was 1. You can see here. This here this 4 was dividing 48 and 1 here, this is GCD of this and this was GCD of, no. The number of elements for which this satisfy will have size GCD M comma N is equal to 1. You can check this. If not, then we can discuss this in next class, like how this is happened. But anyway, any doubts, you can look at it as an exercise for now. But please understand that phi A, number of A bar such that phi A is a homomorphism is a GCD M comma N. Okay, any doubts here? Any doubts for now? If not, then we can stop. This please try. If not, then we can discuss it definitely next time. But for now, I assume whatever we discussed so far, except for this last question, since we are running out of time, whatever we discussed so far in earlier question, is there any doubt? Okay. Please go through this last question. If there are any doubts, please raise it in discussion forum. Otherwise, we will again start with this question in our next next week's discussion session. Okay. Thank you.